Now see, in previous theory we discussed this thing, the velocity of the charged particle is perpendicular to the magnetic field. But suppose the velocity of the charged particle is at some angle theta with respect to the magnetic field. See the figure. Suppose as shown in the figure, the uniform magnetic field that is in x direction, and a charged particle enters in this magnetic field with velocity v at some angle theta with respect to magnetic field b. Then here we have to take two components of velocity v. One component that we have to take parallel to the magnetic field, or we can say in the direction of the magnetic field, and another component that we have to take perpendicular to the magnetic field. Now, we already discussed this thing. If velocity is parallel to the magnetic field, then force will be zero. So here we can write this thing in the direction of the magnetic field. If the velocity component, that is this v parallel, then force due to this velocity f parallel, that will be equal to 0. So we can say this thing, this charged particle will move in the direction of magnetic field with constant velocity v parallel, because in the direction of magnetic field the force is 0. But if we consider this component v perpendicular of the velocity, which is perpendicular to the magnetic field, then in previous theory we already discussed this thing. If velocity and magnetic field are perpendicular, then particle will execute the circular motion. Now here, in this particular case, particle is executing circular motion under the effect of the magnetic force, as well as it also executes the translation motion in the direction of the magnetic field with constant velocity, this v parallel. Therefore, resultantly, the motion of the particle that will be on the helical path. And now if we take the radius of the circular path, then that will be given by the same equation mv upon qb. But here we have to take this velocity which is perpendicular to b, so that is this component. And if this angle is theta, then this v perpendicular component that we can represent by v sine theta. So radius for the circular path of the particle in this case, or we can say radius of this helix, that is given by mv sine theta upon qb. Now, when this particle complete one revolution in the magnetic field, during that revolution, it will be translated in the direction of the field, because in the direction of the field there is no force. So it is moving with constant velocity v parallel. So some horizontal distance is traveled by it. So the distance traveled in the horizontal direction during one revolution, that is called pitch. That is called pitch. So we can write the equation of the pitch P, that is equal to velocity into time velocity, that is v parallel, and time taken to complete one revolution, that is the periodic time. So v parallel, that is v cos theta, periodic time, that is 2 pi m upon qb. In the previous theory we derived this equation. So resultantly we can give the equation of pitch, that is 2 pi mv cos theta upon qb. Clear to all of you up to this one? And the angular frequency and the frequency and periodic time we can give by the same equations which we discussed in the previous theory. So angular frequency omega, that is qb upon m, frequency f, that is qb upon 2 pi m, and period of its revolution, that is t equal to 2 pi m upon qb. Frequency that we also represent by the symbol nu. Clear to all of you?